Okay, in this short video I'm going to introduce cosets, which is chapter 9 of the text. I'll give the basic definition. I'll go over some basic examples, two basic examples pictured here. I'll talk about basic properties of cosets that we'll prove in class, and I'll indicate Lagrange's theorem, a famous theorem in number theory. Okay, well, let me go first to the definition, and this may not make a lot of sense, but when we see the examples, I think you will understand it better. G is a group. H is a subgroup. So it's a smaller set contained in G that's closed under the group operation and under inverse. There are two types of cosets. Left coset of G of H with representative G is defined as the following set. So I take a particular fixed group element and multiply it by every element of the subgroup. So GH is a set. It's not an element of the group, it's a set. Okay. I multiply every element of H on the left by G to get a left coset. Right cosets are similar, except I multiply every element of H on the right by that particular fixed element of G, also a set. All right, well, let's see how this plays out with one specific example. Let me take the integers, so I'm going to take my big group G as the set of all integers. And I'm going to take my subgroup H. In this case, I'm going to do the example of H equals 3Z. Now, we have shown that 3Z is a subgroup of G. It's closed under the operation, which is addition. I'll just indicate that we are using addition here. It's closed under addition. It's also closed under inverse. So H is a subgroup of G. Let me mark all of the elements of H here. There's 0, there's 3, there's 6, there's -3, -6, and so on. So the elements of H I'm indicating by dot. Now remember our definition of coset. I'm going to go ahead and do the left cosets. In fact, in this case, it makes no difference. One particular coset would be 1 plus H. Now remember, I'm using plus because that's my group operation here. In the definition, we used what looked like times, but when we do arithmetic groups with plus, we use plus for our operation. So I can write 1 plus H. This is a coset with representative 1. So what is 1 plus H? Well, it includes 1. What else is it going to include? Remember, I take 1 plus every element of H. So in particular, I could take 1 plus 3. 1 plus 3 is 4, so it includes 4. How about 1 plus minus 3? It includes -2. It also includes -5. Okay, so I indicate the elements of 1 plus H by X. Now, I could also do 2 plus H. Okay, what about the elements of 2 plus H? And I'll indicate those by O. It's fairly clear that 2 plus H is going to be 2 minus 1 minus 4. So notice some facts here. The set H, the coset 1 plus H, the coset 2 plus H are all disjoint, and they comprise the entire group G. In fact, they form a partition of G. And in some sense, these the group and its cosets have the same number of elements. Of course, in this case, it's infinite. But that's an important fact when you have finite groups. Another thing to notice here is that, for instance, I took 1 plus H, and 1 plus H is actually equal to 4 plus H. I could also say that it's equal to 7 plus H. These all have the same number of elements. In fact, if I choose any number in 1 plus H, I could choose -2, -5, and I form the coset associated with that representative. It's going to be exactly the same coset. Okay, so one representative of the coset will generate the entire coset. That's an important fact that we'll see later also. And notice this interesting fact as well. Suppose if I take any two elements of the same coset, let's take -2 and 4, they're in the same coset. So I have minus 2 and 4 are both in which coset? That's right, they're both in 1 plus 3z. Suppose I take minus 2 minus 4. Now, of course, that's minus 6. That turns out to be it's an element of 3z. Right? It's a multiple of 3. So that's an element of 3z. I'm saying 3z is h. Okay. On the other hand, I could take 4 minus 2, and that's 6. That's also an element of h. So what does that mean? It means the difference between any two elements in the same coset is an element of my original subgroup. And you can see that on this picture. If I take any two elements, say minus 4 and 5, they differ by a multiple of 3. So if I take the difference, it's going to be a multiple of 3. It's going to be in h. All right, so what I've just done is shown some properties that are general properties of cosets and shown how they play out with this particular example. Okay, let's go to another example, even and odd permutations. In this case, my big group, G, I'm going to set G equal to Sn. Now remember, that's the set of all permutations on n letters. I'm going to leave n non-specific. I'm going to deal with that degree of abstraction. So this is all permutations on n letters, okay? And my H is going to be the set of even permutations. Now I think that we proved already that the even permutations do form a group. Recall that even permutations are permutations that can be written as a product of an even number of transpositions. All we need to check is closure under the group operation and under inverse. The product of two even permutations is going to be an even permutation. And the inverse of an even permutation is an even permutation. So H is in fact a subgroup of G. Okay, let's form the cosets. Okay, so I could take to take a coset. What I have to do is I have to take an element little g in Sn, and then multiply it by every element in this subgroup. Okay, so let me try G is equal to the transposition 1, 2. Okay, so a coset is going to be 1, 2 operated on every even permutation. All right. Now, if you think about it, every single one of these permutations is going to be odd. And in fact, since there's just as many odd permutations as even permutations, 1, 2 times an is going to be, in fact, the entire set of odd permutations. Okay. Now, is 1, 2 the only choice? No, we could choose 3, 4. 3, 4 times an. These are also all odd permutations, and includes every single one of the odd permutations. So all we have to do is choose one representative from the coset, multiply it by our original subgroup, and we'll get the coset again. Now, suppose we take, we have two elements here. We have 1, 2, and 3, 4. Suppose we took 1, 2, and we took the inverse of 3, 4. What will we get? Well, that's the same as 1, 2 times 3, 4, because we know the inverse of a transposition is itself. And this is actually an element of an. So we see the same property we saw with the integers, that if I take any two representatives of a coset and I operate the one on the inverse of the other, I'm going to get something from the original subgroup. In fact, all the properties I went through that hold for cosets in the integers also hold for cosets in this case. So I'm going to go to those properties and we'll summarize those. Okay. So here's the set of properties that you'll prove in class. Now, to understand this, it's good to think about these in the context of the two examples that I gave you. So what this is saying is, let H be a subgroup of a group G. Suppose G1 and G2 are in G. The following conditions are equivalent. So when we did this before, H was 3Z, G was Z, G1 and G2 were two integers. So the following conditions are equivalent. First of all, G1H equals G2H. What that means is they're in the same coset. Okay. Okay. Property 2 says that G1 inverse G2 is in H. Okay. That's what I showed. Remember, I said that 1 and 4 are in the same coset. So that's in this case it would be minus 1 plus 4 is in the subgroup 3Z. Okay. So that works. And I also did it for permutations. If I take two odd permutations, and I take the inverse of 1, operate on the second, that's going to give me an even permutation. Okay, so that works for both of our cases. In fact, we can prove it in general for any coset. Right? These two conditions are equivalent to the following condition, that G2 is in the coset generated by G1. Okay, we saw that in our two examples. That's also equivalent to the fact that the coset of G2, the coset generated by G2, is a subset of the coset generated by G1. In fact, they have to be equal. That falls out of the equality of all these conditions. Now here's one I didn't talk about, that two cosets, the two left cosets are equal if the corresponding right cosets with the inverse are also equal. In the particular cases we looked at, this is not so significant, but for non-abelian groups, this can be a very significant fact. Okay, so I've given the setup here for Lagrange's theorem. All right, so this is going to formalize some things we've already talked about. I'm representing here the entire group G as this big sausage. Okay, and this subgroup H is a slice of this big sausage. Okay, so this is supposed to be a slice here, and the subgroup H is this end piece here. Now the identity is always in the subgroup, so the identity must be in this slice, and I'm taking one particular point in this subgroup, so I'm calling it little h. All right, now if H is not the entire group, there must be some G1 outside of H, so I've chosen G1 here. And I can form the coset associated with G1, the coset G1H. So that's this here. Now that may not exhaust the entire group. For instance, in the case of 3Z, we had more than one coset. So if I have G2 here, then this coset is G2H. All right. Now what Lagrange's theorem says is that if I take this element H here, there's a corresponding element in this coset, which is G1H. There's also a corresponding element in this coset, which is G2H. In fact, every coset has a corresponding element. If you apply this to every single element of the group little h, then we have a one-to-one correspondence between the elements of H and the elements of each coset. What does that mean? That means that each coset has exactly the same number of elements as the number of elements of G. So I can write that the number of elements of H is equal to the number of elements of GH for any coset. And that's also true for right cosets, so the number of elements of H is equal to the number of elements in any right coset. All right, just quickly, what that means is that H basically divides G up into equal pieces. Okay, so for instance, here I have 1, 2, 3, 4, 5 pieces that divides G up. But what that means is that the number of elements of H must divide the number of elements of G. So that's an extremely important fact, that the number of elements of a subgroup divides the number of elements of the group.